Understand how scenario models can assess future flood and demographic risks. Identify data and tools used in urban scenario modeling. Learn how to communicate uncertainty and adaptation strategies. Learning objectives we will achieve by looking at some key concepts, methods, and frameworks, and mainly by looking at some case studies. Key concepts we have to understand when talking about scenario modeling for flood and population pressures are scenario planning and future uncertainties, hydrodynamic and demographic modeling integration, spatial risk assessment frameworks, urban resilience and adaptive capacity indicators. Scenario planning helps explore how ecological processes, land use patterns, and cultural landscape values may change under uncertain future drivers such as climate impacts, demographic shifts, or policy transitions. By developing contrasting landscape scenarios, planners can assess the resilience of green infrastructure networks and identify spatial strategies that maintain ecosystem functions across multiple futures. Climate-related uncertainties, particularly flood regimes, drought risk, and habitat fragmentation, require integrated spatial simulations combining ecological models, hydrological projections, and participatory stakeholder knowledge. Scenario workshops also support co-creation with communities, enhancing legitimacy and helping to visualize landscape transitions through maps, storylines, or design visions. Ultimately, scenario-based approaches strengthen landscape planning by revealing robust adaptation pathways that protect ecological integrity while supporting cultural and socio-economic needs. Integrating hydrodynamic and demographic modeling enables planners to evaluate how changing population patterns interact with future flood dynamics and other water-related risks in a more comprehensive and forward-looking way. By linking population projections, such as urban growth, densification trends, migration patterns, and socio-demographic characteristics, with hydrological and hydraulic simulations, planners can identify areas where increasing development pressure may significantly raise exposure to inundation, intensify runoff volumes, or alter natural water flows through land use change. This combined modeling approach makes it possible to anticipate not only where hazards are likely to occur, but also which communities, infrastructures, and services may be most affected under different future scenarios. Such integrated models are particularly valuable in landscape planning because they reveal opportunities for spatial strategies that reduce vulnerability while supporting ecosystem functions. For example, simulations can demonstrate how ecological corridors, floodplain restoration, natural vegetation buffers, wetlands, and multifunctional green infrastructure networks can slow water movement, enhance infiltration, and create safer settlement patterns for both existing and future populations. At the same time, combining hydrodynamic and demographic datasets supports scenario-based decision-making by allowing planners to test how alternative development pathways, such as compact urban growth versus dispersed expansion, may influence long-term risk exposure under varying climate projections. Ultimately, this integrated approach strengthens climate adaptation strategies by aligning spatial planning decisions with water system dynamics, enabling more resilient, sustainable, and socially equitable territorial development. Spatial risk assessment frameworks help identify how environmental hazards, exposure, and landscape sensitivity overlap in space, enabling planners to prioritize areas for adaptation or protection. Integrating GIS-based hazard modeling with ecological and socio-economic indicators allows these frameworks to reveal spatial patterns of vulnerability and support evidence-based land use decisions. In landscape planning, such tools are essential for understanding how green infrastructure, natural vegetation, and settlement structure influence risk distribution across different future scenarios. Spatial analysis of hazards, modeling of natural processes, flooding, erosion, heat, storms, etc. Hydrodynamic, hydrological, or climate models as the basis for developing risk maps. Assessment of hazard intensity, frequency, and spatial distribution. Exposure. What is located within the risk zone? Population density, development intensity, and infrastructure. Particularly vulnerable sites. Schools, hospitals, cultural heritage objects. Forecasting future exposure, demography, urbanization. Sensitivity. Ecological characteristics of the landscape. Soil type, vegetation structure, habitat quality. Socio-economic factors. Income levels, age structure, mobility. Technical and engineering systems, water management, drainage, road networks. Vulnerability is a combination of hazard plus exposure plus sensitivity. Spatial vulnerability index. Easily interpretable vulnerability layers, multi-criteria evaluation. Focus on locations where multiple risks overlap. GIS-based flood risk mapping provides a spatial foundation for assessing hazard extent, depth, and frequency, enabling planners to evaluate how different landscapes and settlement structures may be affected under changing climatic conditions. When combined with population projection and land use change models, these tools help identify future exposure patterns by linking demographic growth, densification, or suburban expansion with potential shifts in territorial vulnerability. Multi-hazard visualization techniques further enhance understanding by integrating floods, heat stress, erosion, or storm impacts into layered risk maps that highlight cumulative pressures on urban and peri-urban systems. Participatory scenario workshops with stakeholders strengthen this analytical base by incorporating local knowledge, community priorities, and value-driven perspectives, making future scenarios more legitimate and actionable for planning practice. International examples illustrating diverse approaches to climate risk reduction and adaptation demonstrate how cities and regions apply context-specific yet complementary strategies to address complex environmental challenges. These include the Thames Estuary 2100 strategy in the United Kingdom, which focuses on long-term adaptive flood risk management and integrates defense upgrades with landscape and community benefits. Jakarta's Coastal Adaptation Strategy in Indonesia, which combines large-scale engineering measures with nature-based and community-level interventions to respond to sea level rise and land subsidence. The Copenhagen Cloudburst Management Plan in Denmark, which adopts a blue-green infrastructure approach to manage extreme rainfall through surface-level drainage, urban waterways, and multifunctional public spaces. And New York City's 1NYC resilience scenarios in the United States, which emphasize strengthening infrastructure systems, social resilience, and climate-adaptive urban governance. Together, these examples illustrate that effective climate adaptation requires integrated planning frameworks, cross-sector collaboration, and the combination of structural, ecological, and social strategies tailored to local environmental, spatial, and socio-economic conditions. One of the case studies is the Thames Estuary 2100 plan. We need to adapt to climate change along the Thames Estuary. As sea levels rise and defenses get older, the risk of flooding from the Thames increases. The Thames Estuary 2100 plan outlines how to manage this risk. Developed by the Environment Agency and its partners, the plan sets out a vision for the estuary's future. The most significant benefit of the Thames Estuary 2100 (TE 2100) plan is managing the risk of tidal flooding. This will make people and property safer. It will also avoid disruption, for example, to schools, hospitals, power supplies, roads, and rail lines. Managing flood risk as sea levels rise will mean reshaping our riversides. This is an opportunity to create additional benefits. We want to provide benefits to people, the economy, and the environment. Some examples of benefits include better opportunities for leisure and recreation, such as riverside paths, improved health and well-being, for instance, by creating more green space for people to enjoy, creating a new wildlife habitat, natural carbon storage, for example, by creating salt marshes, protecting landscapes, protecting historic buildings, such as the Tower of London. The Environment Agency has worked with partners to agree the benefits we will create together. These benefits sit at the heart of the Thames Estuary 2100 plan. The Thames Estuary 2100 plan introduces the Riverside Strategy approach. This approach integrates upgrades to flood defenses with riverside improvements and wider benefits. Riverside strategies are visions for a stretch of riverside. Councils or other organizations can create riverside strategies. For instance, organizations interested in riverside development and improvement may produce a strategy. Riverside strategies should be an integral part of statutory local planning. They can be standalone documents or form part of a local plan. You should create them in collaboration with local communities. They should include community ambitions for the riverside. Jakarta's mitigation of land subsidence is driven by international assistance and sharing of lessons learned with other delta cities, as well as acknowledgement of the need for an integral water management approach, in which sanitation, wastewater treatment, surface water quality, alternate access to clean drinking water, and flood protection are being improved in an interconnected way. This approach is particularly relevant if a city has a significant portion of land at, or already below, sea level, is highly canalized, or has a high rate of groundwater extraction, and the delta is no longer naturally being reinforced with sediment. The government of DKI Jakarta Province, Daerah Khusus Ibu Kota Jakarta Raya, or Special Capital City Region, has taken numerous measures to adapt to and manage flood risks. These measures range from building a seawall on the shoreline, to dredging rivers and lakes, to providing reforestation support to neighboring cities upstream. At the community level, via modest actions, urban poor people and informal dwellers also implement individual adaptation and flood protection strategies. Before 2017, Jakarta's flood management strategy focused on normalization, which involved constructing embankments and concrete walls along the Kali Ciliwung and other rivers, and responding to flood-affected settlements primarily through relocation and the construction of rumah susun, low-cost apartments. Emergency measures relied heavily on water pumps at floodgates to push excess water into canals, supported by a rainbow team structure in which the blue team handled inundation, the orange team addressed cleanliness such as clogged drains, and the green team worked on urban greening. After 2017, the strategy shifted toward naturalization, aiming to slow water flow from upstream by creating infiltration wells and greening floodplain zones. Instead of relocating communities, the city began applying land consolidation approaches that allow residents to remain in place while improving conditions, with local people actively involved in preparing community action plans. Emergency response also evolved toward vertical drainage solutions that direct water into the soil via infiltration wells, while the rainbow team continues to operate with increased community participation. The Cloudburst Management Plan introduces a highly innovative, blue-green approach that strengthens Copenhagen's long-term resilience to extreme rainfall while creating direct social and environmental benefits. By combining ground-level drainage, new canals, urban waterways, reopened streams, and landscaped storage areas, the city can manage high water volumes more efficiently and at significantly lower cost than relying solely on sewer system expansion. These solutions not only reduce economic damage from 100-year rainfall events but also enhance public spaces, create recreational green-blue corridors, and integrate stormwater into everyday urban life. The plan's emphasis on risk dimensioning, allowing up to 10 centimeters of water on roadways during extreme events, and its prioritization of ground-level drainage wherever feasible show a shift toward flexible, adaptive measures that work with the city's existing spatial structure. The plan directly acknowledges Copenhagen's demographic and spatial diversity, recognizing that densely built areas require different tools than neighborhoods with more open space. In compact districts, large subterranean tunnels carry cloudburst water directly to the harbor, whereas in less dense areas, surface-level floodways and green infrastructure can be implemented more easily and at a lower socio-economic cost. The strategy relies on several key instruments: detailed flood risk mapping, division of the city into 26 water catchment areas, prioritization based on risk and ease of implementation, coordinated planning with neighboring municipalities, and a long-term financing framework combining utility revenues, municipal taxes, and private responsibility for property-level protection. Through this integrated set of measures, Copenhagen builds a coordinated system capable of handling increasing rainfall while improving everyday livability for residents. As a resilient city, New York will be able to respond to adverse events like Hurricane Sandy, deliver basic functions and services to all residents, and emerge stronger as a community, to eliminate long-term displacement from homes and jobs after shock events by 2050. The city will upgrade private and public buildings to be more energy efficient and resilient to the impacts of climate change, adapt infrastructure, such as transportation, telecommunications, water, and energy, to withstand severe weather events, and strengthen our coastal defenses against flooding and sea level rise. We will strengthen homes, businesses, community-based organizations, and public services to reduce the impacts of disruptive events and promote faster recovery. New York City's vision for a resilient future focuses on ensuring that its neighborhoods, economy, and public services are prepared to withstand and emerge stronger from the impacts of climate change and other 21st-century threats. This commitment includes making every neighborhood safer by enhancing community, social, and economic resilience, upgrading buildings to withstand evolving climate risks, adapting regional infrastructure systems to ensure uninterrupted services, and strengthening the city's coastal defenses to protect against flooding and rising sea levels. This plan enhances the focus on strengthening communities by building the community, social, and economic resiliency of our neighborhoods. It will include a new emphasis on deepening resident, nonprofit, and business participation in emergency planning, and exploring social cohesion as a strategy for resiliency, which would consist of forming a task force to study the role of community institutions, like houses of worship and community-based organizations, in resiliency planning. Integrating climate and population data has become a fundamental component of contemporary resilience-oriented planning, as it enables a more precise understanding of how environmental hazards intersect with human systems. Climate datasets, such as projections of extreme precipitation, temperature variability, sea level rise, and flood frequency, provide insights into the physical dynamics of risk, while demographic information reveals patterns of exposure and social vulnerability. When combined, these datasets allow planners to move beyond purely hazard-focused assessments toward a more comprehensive evaluation of risk that considers who is affected, where impacts are likely to occur, and how vulnerability may evolve over time. This integration is particularly important in rapidly urbanizing regions, where demographic change can significantly alter risk landscapes within relatively short timeframes. Population growth, migration trends, aging populations, and shifts in settlement density all influence the scale and distribution of climate-related impacts. For instance, increasing urban densification in flood-prone areas can intensify both direct exposure and indirect consequences, such as infrastructure disruption and reduced emergency response capacity. By incorporating demographic projections into climate modeling workflows, planners can anticipate these dynamic interactions and design proactive adaptation strategies rather than relying solely on historical data. Moreover, integrating climate and population datasets enhances the ability to conduct scenario-based assessments, enabling decision-makers to test how different climate trajectories and demographic futures may interact. Such approaches support long-term strategic planning by identifying robust adaptation pathways that remain effective under multiple uncertainty conditions. Ultimately, climate population integration shifts planning practice from static risk mapping toward dynamic, future-oriented resilience planning grounded in both environmental science and social realities. Within spatial planning, demographic data plays a critical role in translating risk analysis into actionable land use and infrastructure decisions. Population characteristics, including density, distribution, age structure, socioeconomic status, and mobility patterns, provide essential insights into how different communities experience and respond to environmental hazards. When integrated into spatial planning processes, these datasets help planners identify areas where adaptation measures are most urgently needed and ensure that interventions address both physical risk and social equity considerations. Demographic information also supports more nuanced zoning and infrastructure planning by revealing patterns of future development pressure and service demand. For example, projections of population growth and urban expansion can inform the allocation of land for housing, transportation networks, green infrastructure, and emergency facilities, ensuring that spatial plans remain responsive to evolving settlement patterns. Similarly, identifying concentrations of vulnerable populations, such as older adults, low-income households, or communities with limited mobility, enables planners to prioritize investments in climate-resilient infrastructure, accessible evacuation routes, and socially inclusive adaptation strategies. Furthermore, integrating demographic data into spatial planning contributes to more effective monitoring and evaluation of planning outcomes over time. By tracking changes in population distribution alongside environmental indicators, planners can assess whether implemented measures are reducing vulnerability, improving accessibility, and supporting long-term sustainability goals. In this way, demographic analysis functions not only as an input for planning decisions but also as a continuous feedback mechanism that helps refine spatial strategies in response to changing socio-environmental conditions. Effective scenario modeling is often constrained by significant data-related challenges that limit both analytical accuracy and practical usability in planning processes. One of the most common issues is the lack of consistent long-term climate records, which makes it difficult to identify reliable trends or to calibrate predictive models for future conditions. In addition, datasets frequently exist in incompatible formats, use different spatial scales, or vary in temporal resolution, preventing meaningful comparison across regions or time periods. Such inconsistencies complicate the integration of multiple data layers, such as hydrological, climatic, and land use information, into coherent modeling frameworks. Demographic and socio-economic datasets present further limitations, as they are often outdated, fragmented across institutions, or collected using different methodological standards. As a result, linking population characteristics, such as age structure, income levels, mobility patterns, or settlement density, with climate variables becomes technically complex and analytically uncertain. These gaps make it difficult to construct comprehensive vulnerability assessments that simultaneously account for hazard exposure, social sensitivity, and adaptive capacity. The problem is compounded by unclear metadata, missing documentation, and uneven data quality, which undermine the transparency and reproducibility of modeling results. In many cases, restrictions related to data ownership, licensing, or privacy regulations further limit access, preventing planners and researchers from testing alternative scenarios or sharing models across sectors. Together, these constraints reduce the precision of projections and increase uncertainty in scenario outcomes, potentially leading to planning decisions that overlook local variability or fail to represent the needs of different communities. Addressing these challenges, therefore, requires not only improved data collection and standardization but also stronger institutional cooperation, open data policies, and investment in interoperable digital infrastructures that support more reliable, inclusive, and adaptive scenario modeling.